Hello, everyone. We have two presentations, and since we're running a little bit, if we can get the clock going, a little bit behind time, I'm going to keep it very brief here with the introductions. The first presentation is Hojat Yeganeh from IMAX. He received his PhD from the University of Waterloo in Canada in 2014 and is currently a senior member at IMAX Labs. He's also a senior member at the IEEE and has tackled a wide range of challenges in the video industry, including HDR video quality assessments, tone map video quality assessments, banding detection, video enhancement, and very importantly, film grain similarity measurements. His significant contributions to perceptual video quality assessment earned him an Emmy Award. Hojat has also published numerous papers and holds dozens of patents in this field. Today, he will present a paper that proposes a novel perceptual quality assessment method to identify and quantify noise patterns. And I'm very curious to learn more about it. First time I heard about film grain synthesis was about 20 years ago, so this is like a blast from the past. So I'm very interested to hear what happened in 2 decades. So please welcome Hojat.
Thank you, Mike, for the introduction. So we have been in great sessions in SIMT, and if I wanted to take away one message is the preservation of creative intent. So some people, they wanted to preserve the audio part of it. Some people, they wanted to preserve the skin tone and other aspects of the creative intent. And you guys, you agree with me as the cinematographers or people who work on the creative side that like directors or like a creative, they still love the look and feel of the analog film grain or the analog film. And the essence of the analog film to date is one of the biggest essence of that is film grain. And they love film grain. The emulsion, the silver halide that gets to the real metal because of the exposure of the light. And they love to have that. And it appears like a film grain in the negatives. But what happens in the streaming board? They actually ignore that, right? So it's not compression friendly. It's a very high entropy signal. They don't like it. So what they do denoising or degraining or whatever. And then they come up with the clean content and they stream that clean content. Is there any solution to it? Well, maybe they can spend a huge amount of bits. How can I get to the next slide? Oh, okay, cool. There is an elegant solution, they have proposed an elegant solution to mitigate this issue or somehow overcome the issue of this kind of compressing a very high entropy signal, and that is the idea of film grain synthesis. So what do? They start with denoising the content. And then they come up with a model, like some statistical model on the grain or the residual, and they put it in the form of a metadata along with the video stream. So they compress the clean content, and then they add the grain back after doing the decoding. So they do decoding, and then the device uses the metadata to do the regraining. So this is a very elegant solution. This is a very interesting solution. But it works like if I wanted to talk about mechanics, it works like this. So they create a template, a noisy, grainy template, and they wanted to use that template to do regraining. If you forget about math, the basics is that they generate the template, and then they randomly select some blocks out of that template, and then they put those blocks next to each other, side by side, in a kind of a sliding fashion, and they fill up the whole frame using these blocks or film grain, or those random noisy patterns that they've generated, and they call it template. And of course, recently they do some local adaptation as well, because like if you look at the physics of the film grain, the original film grain, it depends on the luminance, like the exposure of the light. So the exposure of light, the different exposure of the light can create different kind of like a particle size or halide or silver halide. So you see different look and feel of the film grain in the low luminance area or high luminance area or a mid-tone. So this, like the metadata today, or the AFGS1 metadata that is used by like AV1, gives a user some sort of a flexibility to play with the local adaptation. Say, I need that much grain in this luminance area, that much grain in this luminance area, or maybe forget about any film grain on the highlight. Somehow to like mimic the physics of the true film grain. But what happens in reality? So the pipeline is there. It's an elegant solution developed by the streaming companies or so. But one thing that is happening in reality, as a content creators, they see some sort of a repetitive pattern or periodic pattern. This is a very known issue with AFGS1, like a film grain synthesis approach, or any sort of film grain synthesis approach that uses the same kind of mechanics or approach, that is generating a template and then selecting some like a block size randomly and then putting it like next to each other on the decoder side. So like if I wanted to be an extreme side, and explain why this repetitive pattern exists or why this is happening. Imagine that the block size is the same as the size of the template. So you're putting a template in on one side of the frame, and then you're repeating it, and then repeating it, and then repeating it. And that's why you see this periodic pattern or repetitive pattern. So the block size matters. If you choose a block size that is like a smaller, then you have like a less chance of seeing repetitive pattern. If you make the block size bigger and bigger, the chance is getting higher and higher. But like it depends on the content, right? It depends on so many things. Should I do it subjectively? What should be the block size? Today, if you use David spells like DAV1D, but in the community we call it David, or libDavid if you wish, if you're like a FFmpeg user or so. In libDavid or David decoder, which does the regraining, the block size is hard coded to 32 by 32. It's funny is I went back to the code and then I changed that code or look at block size, and I wanted to change it and it didn't work, so it gave me an error. And then I submitted a ticket to David guys saying that, look, I mean, it doesn't work, so it's giving me a very wrong framework. So they didn't think about the importance of this block size on the decoding, on the regraining side. So the reality is that if content creators, they watch this content and they see, well, this is the amazing thing that we did. We saved 30% on savings or on the bitrate values, and then we have an amazing working pipeline. But content creators do not like this. Like I said, they don't like the repetitive pattern. They don't like the periodic pattern. So they never approve the overall look and feel of this content. This is an amazing job done by the standards or by the streaming groups, but they need to think about the other side of it, or look at this problem from the perceptual quality aspect of it, or look at this problem from the look and feel. Because if you can convince the content creators to use this framework, then this framework gradually disappears, or just like what is happening today in the film grain synthesis. This idea has been around for more than a decade or so, but it's still they're struggling with the adoption. Okay, so now the question is that what should be the right block size for a particular content? Should it be like a kind of a subjective thing, so people, they see it and then play with the 4x4, 8x8, 16x6? We say that, we can develop an objective model or an objective metric that penalizes the artifact, this periodic pattern artifact, because it's not always happening as drastic as we think for every content that we see. And we know how to develop objective metrics. We have done so many things, and recently we announced our film grain similarity metric in IBC. What I'm presenting here is one aspect of that film grain similarity metric. It's not the whole thing. We do much more than this, but to give you a very, very specific idea about the problem, I'm presenting this part of the film grain similarity metric. And I encourage you to visit our booth in the hall. And I do have a very, very good demo to show you this repetitive pattern, periodic pattern, or how it works and how it appears on the AV1 existing framework. So what we do, we start from the input frame. So we receive a frame that has kind of a regrained version of the content. We use mean filtering, so we do the average on that. And then we come up with something called normalized frame or residual or something like that. And then we use AV1 metadata that is embedded in this stream, and we try to reproduce the template, like what David did. And then we use this grain template and we move it along on the normalized frame, and we compute cosine similarity. So what does cosine similarity tell us? Cosine similarity measures the angle between two vectors. It doesn't care about the absolute value of the vectors. It cares about the angle of the vectors. So if we see they are on the same side, or the angle is 0, then the cosine similarity is high. And then at the end, we come up with some sort of a map, a absolute cosine similarity map. So the white part shows that we see more kind of a repetitive pattern. The black side shows that no, there is no repetitive pattern. So I don't want to go deep into the map or so, but again, if you really wanted to see what's happening in the film grain synthesis part, so this Y bar is the result of the film grain synthesis, which means that we do have a grain template, and then we do have a clean kind of content that is received by the decoder, and the decoder job is to add this kind of f of y, which is like the local adaptation, and the grain template plus the decoded content. Once you receive the frame that is already regrained, we don't have the clean content. That's why we take the mean frame or the average of that frame as a proxy to that kind of clean content. And then this local adaptation thing is actually helping us to exclude the areas that causes some sort of, or that exclude the area with kind of a textured maskings, right? So those pattern is very obvious on the part that is kind of a flat region or sky or a big section of the wall or something like that. The very next thing that we always do in developing metric is to conduct subjective studies, because you don't want to build a metric that is kind of producing nonsense scores. So something should make sense here and should be aligned with the subjective assessment. So what do? We try to generate or reproduce some test patterns, something that is kind of practical scenarios and real case scenarios. We selected 16 source content that has film grain. To all of these 16 content, they had like a film grain in it. And we selected wisely, not every content that you see with film grain. So we selected the content in a way that if you look at the percentage of the flat region, it's kind of a very high in that sense. So you see the statistics of the flat region percentage. So one of them, it has a very, very big portion of the sky. One of them has like a very flat region on the buildings or a wall or something like that. Or maybe a portrait or very big face focused on the middle of the frame. And then we created the 80 test sets by variation. So like we use SVT AV1 to encode the content, and we use different block size to decode or regrain the content in LibDavid. So we use like a 4 by 4, 8 by 8, 16 by 16, 32 by 32, and 64 by 64. And then this is the MOS. This is the trend of the average MOS. Of course, people, they like the smaller block size over the bigger block size. And it's intuitive, but it's good to hear it from the subjects. One thing that I wanted to mention is that why we asked expert viewers. This is a very important thing. Well, film grain and assessing film grain is nothing that like a typical people can do. Like if it was a video quality assessment, if you really wanted to design a perceptual video quality metric that we did in the past, so you may ask people to come over, like it could be a students, like a naive viewers, typical viewers, to rate the quality with respect to the source. But when it comes to the film grain, not everyone can participate in this subjective study, because the film grain assessment is very, very critical. As the difference in film grain is very subtle. So we relied on IMAX expert viewers, people who spend days and nights on film grain assessment. And then we asked them the similarity between the overall look and feel of the film grain of the source and the test version that we decoded using multiple versions of the block sizes. So 1 means that, well, it's very, very visible repetitive pattern. And 5 means no, there is no visible pattern. It's very close to the source. And this is the mass. So the mass shows if you go lower in the block size, then you get more kind of fidelity to the source. And this shows one of the examples that how the algorithm works. So when we use the pattern, look at the template, and we move it along as a kind of a sliding window fashion, the cosine similarity gives you some peaks whenever you see alignment between these two vectors. And this shows like 2 examples, one with like a 64 by 64 block size, which you see more whites, you see basically more peaks on the map. And then if you use 4 by 4 block size, you see less kind of alignment between the templates and the blocks that you have taken from the frame. We computed the correlation, as we always do with the subjects. And what we did this time, we singled out subjects, like a subject number 1, we computed the mass, and then we computed the correlation of that particular subject with against the mass. And then we repeated that for all the subjects, like subject number 1 all the way to subject number 10. Why we did this? We wanted to know what is the performance of the average subject. Well, and remember, we are dealing with expert viewers here. So we wanted to say that if we design a metric, that metric or that like a measure should be as good as an average expert in the field. So we don't want to come up with a metric that is very, very low performance. So we want the performance to be as good as an average expert viewer. What is the conclusion at the end? So what do I want to say? The organic question that you may ask is that, okay, what's the benefit of using this metric? What do you want to say here? We know that AV1 is using 32 by 32. Every display that you buy today that has this capability of AV1 with film grain synthesis, it suffers from the same issue. No matter if it is a very high-end TV or it's like the other, like a stick or whatever, or even the player, software player. Why? Because they all use data to decode this, and they all use the hard-coded block size, which is 32 by 32. For some content, you may not see that severe periodic pattern, but for some content you may. For some frames, for some scenes, you may not see that, but for some scenes, you may see it. What we are proposing here, we are with this metric to propose one thing to the community. We wanted to say that we as like a content, not content creators, we are IMAX, we are not content creators, but we care about quality. We care too much about preservation of creative intent. It's our job to give the streaming world feedback on what they are doing. So, and then help them. If we really care about preservation of creative intent, we need to bridge this gap. They don't talk to us. We don't talk to them so often, but we really need to get them to know these things and talk to them more often. So here is one of the chances. So if we are not happy with the look and feel of the AV1 regrained version of the content, we need to go back to them saying that, hey guys, you are putting a lot of metadata in this, like the AFGS1 metadata, it contains this, the luminance, whatever. Add the block size as another parameter for the metadata. And because the block size matters, And then as part of the content creation or the metadata creation, we can use such metrics like this. I mean, there is no need for subjects to watch and assess what is the right block size. We can run this metric, and then we can come up with the optimum block size for that specific content, and then we can put it in an AFGS from metadata and then transmit it. And the decoder side and the display side, they can also read the block size from the metadata, and then when they do regraining, they use it with the different block size or with the optimum block size that is hidden into the metadata. There is no need for just a hard-coded value like a 32 by 32. So, yeah, that was my talk, and happy to answer any question if you have.
Thank you, Hojat. I know this question, Ben, and then Bill. I think there's some microphone.
Who do you want first?
Ben would be good, audio.
Hi, Ben Wagoner, Prime Video. So, this is awesome research. Thank you so much. This is answering some good questions here. Are there issues with kind of like edge threshold things when you're very small blocks? I wonder if you're doing like a Super 16 at 4K where, you know, you're it's not like random noise. It's like you actually have like physical particles almost you're being emulated there. Do you get weird issues with a too small block size by having particles cut in half and that kind of stuff?
That's related to the overall metric that we have implemented. So this is a very, like, it's a kind of one aspect of that metric that cares about this kind of issue that I just talk about it. But for that, so what the metric does, it assumes that like whatever is in the source, it's in the source is the ground truth. So it's a full reference metric. It's not like this. It's not a no reference metric. So it's a full reference metric. We care about like whatever we see in the source as the ground truth, and then we take the test and then we run the film grain similarity metric on it to see how close that is to the original source. Here we are not saying that like the particle size should be like this or should be like that or something. You say, well, whatever you give me as a ProRes in the format of JPEG or 2000 or whatever, that's the original source, and we wanted to preserve that creative intent. So the film grain similarity metric, the overall film grain similarity metric, not the one that I presented today. The job of that metric is to give you this sense or any sort of to penalize any deviation from the source.
Right. So you don't have issues with very small block sizes being used at the 4x4, that's there, causing these shape changes?
No.
Awesome. Thank you.
Hey, Walt, who said Dolby? Can you go back to your conclusions? So you speak to frequency filtering, but AFGS1 doesn't support frequency filtering. Can you speak to that?
Yeah, so here we wanted to make the problem, generalize the problem. So we wanted to say that this problem is not exclusive to AV1 or this AFGS1. So even like if you think about the frequency filtering or auto-regulating, both, they work on the fundamental of, or they are based on generating a template and then randomly select some blocks out of that template. It could be frequency filtering, it could be autoregressive. Well, you're right, AFGS1 today doesn't support frequency filtering, but like this problem is more than just AFGS1 metadata or autoregressive formulation or so. Any sort of film grain synthesis that works on the pattern, like generating a template and then randomly we select some blocks out of it, is susceptible to this issue.
So following up on it, for instance, the newer MPEG SEI messages allows far larger block sizes, but once you get to a certain size block, then the randomness of the image or the randomness of the block is larger, and therefore the block should be less sensitive. Is there a point where there's sort of an inflection where it starts going back up again as you get to a larger block? I mean, you were limited to 64 by 64, but you can get much larger on the MPEG SCI messages.
Well, I mean, based on what we did, first of all, this method is agnostic to the block size. This method is based on the math and like mathematical formulation that we propose. And then the reason that we tested 64 by 64, it was because it was very handy to us, and then we could do it. And we wanted to reduce the length of the subjective study, but that's why we didn't go even like a further than like a 128 by 128 or so. But based on the math, if you increase the size of the block, and then you make it very, very similar to the size of the template,
Right.
Again, this problem appears. There is more chance to see this problem, this periodic pattern, repetitive pattern.
Okay. And then finally, on the last one, you didn't show any data, any correlation between the content and the block size. Can you speak to that?
The content and block size, yeah, that's a good point. Yeah, we don't have, but like we saw that when we deal with the content with a lot of textures and very low and flat region, so the importance of the block size is lower than when compared to the content with like a big portion, like a big flat region. So if you're dealing with faces, and again, I refer you to come to drop, and I recommend you to drop by our booth or so and look at the demo that we have created. So you clearly see on the faces when you see crowd, and like in the repetitive pattern doesn't exist on the faces of the crowd. But look, you see sky, and the repetitive pattern is very obvious on that blue sky. Yes, there is. We realize that there is a very good correlation between the repetitive pattern or seeing this kind of repetitive pattern and the underlying content.
I think Bill had a question as well.
Hey, thank you for this presentation. One comment, one question. One comment, I've attended other talks on film grain synthesis and was extremely concerned by the apparent equivalence on the part of a lot of researchers between noise and film grain. Film grain is fundamentally at a quantum level absolute data. It is the signal. The consideration and modeling of that as noise is a fallacy and trends to very bad decisions and results. So I like the notion of modeling grain as grain. That's key and an important differentiation. And end of commentary. Question. Often you see content with film grain synthesis that makes it look like ants are crawling around on the screen. Is there an extension foreseen to this metric that contemplates consecutive frames, so a temporal component?
We have to consider the temporal aspect of it because the organic motion of the grain is something that, again, creative care about it. Right now, there is no temporal aspect into this, neither this one or the overall film grain similarity metric that we have proposed recently and we presented in IBC. Yeah, that's the gap. So we are working on it.
Hi, Susie Han from Center. If you go to the conclusion page, maybe I missed this, but just wanted to understand how it works out in terms of workflow. So it says that you recommend adding metadata for the block size.
Yeah, one item to the metadata. Right now, the metadata is very busy and crowded or something, so they have many lines of doing this kind of autoregressive coefficients and the luminance adaptation. Okay. That's fine. Everything looks good. Scaling factors, like a grain scale factor, whatever. Add one more, and that is just the block size. And that block size matters because when you decode, or you add the grain back after decoding, the block size matters and it avoids the repetitive pattern.
So without the metadata, you think the decoder cannot handle the smaller blocks. So it's just like a flag on and off. Hey, I'm not using 32.
I think the reason that the hard-coded 32 by 32 is because of, because the 32 by 32 was the right block size for those tested frames, by the way, it's not only dependent on the content, but also it depends on the resolution as well. So 32 by 32 may work for 1080, but or for other resolution, but it may not work for the UHD or vice versa. So it's complexity, I think, to me. So the complexity, if we wanted to run it on the device, maybe they did some sort of a performance measurement. They realized that, 32 by 32 is the optimum size. But if you think about the creative intent, or if you think about these funky patterns, then I would say, well, you know what? This is a handshake that should happen between the creative side and the streaming side. And then these are the gaps that we need to work on. So you guys, you work on make it faster somehow, but like this is nothing to be acceptable by the content creators, because content creators, they don't tolerate this like a funky repetitive pattern.
But then maybe this will impose some dependency on the decoder side. So
it's just libDavid, right? So like even today, David is used in the decoder side. Why I'm saying that you can easily compile libDavid with this addition of to the this is what we did actually. We added one parameter to the metadata, and then we change the code up with libDavid, and libDavid sees that additional metadata, blocks us. When David does the read graining, it uses like the blocks as that is hidden into metadata. But there is 4 by 4, 16 by 16, whatever. And it's truly content dependent and resolution dependent.
But the hardware has to be updated, right, for doing this?
Yeah,
that's okay. Thank you.
All right. And I think we're at the end of time. Thanks so much, Hojat.
Thank you. Thank you, everyone.